So once again, welcome. Here's our program timeline as of right now. Today is the 15th, so we're having our kickoff meeting. We would like to have a general idea of what your experiment is going to be. All it has to be is about a paragraph long, just saying what it is that you want to test or collect data about, and how you presume to go about doing that. Then we'll have another meeting on the 30th to kind of go over some of those concepts. We'll give some pointers on maybe refining it slightly, and we'll be able to answer any questions that you have at that point as well. Then on October 15th will be time for the logical design, which is essentially, what is the experiment? How is it going to work? What are the sensors that you're going to use in order to collect that data? Then on November 1st, we're going to want a physical design. So this is the actual, specific details of the equipment that you're going to be using. So that'll include like a wiring diagram, all of the sensors, the exact sensors that you're going to be using, the Arduino board that you're going to be using. And then at that point, we're going to choose which ones will be flying on the Blue Origin rocket. Now, we do have some other platforms that we may be working with as well. So, certain types of sensors will lend themselves to different types of platforms. Certain sensors might work better on, say, a high-altitude balloon or a glider, whereas other things might work better on on the rocket itself. And I'll go into a little bit more detail about that a little bit further down in this presentation. Then we're going to have our third and fourth meetings on the 15th and the 30th of November, which will be probably mostly doing troubleshooting, helping folks to actually build those engineering models based on that physical design. Some of you might not need any help. That's great, but we're going to be available for you should you need it. Also, you don't have to just save all of your questions for the meetings. You can always send me an email, and I will try to answer your questions that way. We can organize times to have individual meetings or phone calls, but we'll have actual meetings on those dates just to, be available in person virtually. And then December 15th is when we want to have your actual engineering builds completed. Now, keep in mind that we're not going to fly the actual things that you make. We are going to build it out of flight-ready parts and build it into the actual 2U cube frame. So let me just stop presenting for a second. You guys can still see me, right? Pretty good? Or is my picture really small because there's so many people in here?
You are still sharing.
All right.
I can still see you.
Yeah, I might just be a tiny little thing. So let me stop presenting for a second. And then I think you can actually pin me so that I show up. If you hover over my picture and then you click the pin, then my picture will become a lot bigger and it'll be easier for you to see some of the things that I'm going to show. So right here, this is an actual 2U cube frame that we flew on Blue Origin. So we need to we're going to try to fit about 6 experiments in each of these, as opposed to the 1U cube frames that you guys are used to working with. All right, so we're going to take multiple experiments that you guys design and build, and we're going to try to fit them inside of here, as many as we can fit within the constraints that exist. And we'll go over what those constraints are. All right, let me go back to presenting. All right, and then by January 15th, we expect to have all testing done on the built to use, and they'll be ready to fly by then. All right, so we will be launching aboard Blue Origin's new Shepard. For those of you who didn't see, actually, last week, they got to do a really cool test of their launch escape system, because it just so happened on their launch, which was a payload launch, it didn't have any people on it, their booster actually experienced an anomaly, and they detached the capsule at an extreme velocity. It actually made it kind of look like the entire booster exploded. But if you look at the frame by frame, it was just all of the flames coming out of the engine on the bottom of the capsule that engulfed the rest of the booster to make it look like it was totally on fire. But it was really, nobody wants to lose a booster, I'm sure, but it's really important that their capsule's escape systems work, because if there were people on board, they got to get that thing away from the booster if something bad is going to happen. So fingers crossed that it doesn't have any impact on any of our launches at the beginning of next year, but we'll keep you guys up to date as we find out information about that. All right, so on board that new Shepard rocket is going to be a payload locker called a feather frame, and that's what we have here on the right. And if you look there, you can see that there are 12 nanolabs inside of that feather frame, and a nanolab is this 2U cube frame. It has a USB connector on top that will provide power, and then they'll stick 12 of those inside of there. So keep this in mind while you're developing your experiments. On board New Shepard, your experiment is going to be inside of this payload locker, which is going to be enclosed. There are some vents to allow air in there to kind of keep things cool, because it can get real warm in there. And that payload locker is going to be inside a pressurized capsule. So again, keep that in mind when designing experiments, and just know that those are going to be the conditions. So if maybe you wanted to get atmospheric data, then this platform might not be the best platform, unless you want to kind of figure out or look at the data of what happens inside of that capsule during flight. There might be changes in air temperature, air pressure. So don't think that you can't use those types of sensors, but just be aware that that's the situation. If you instead wanted to, do a high altitude balloon mission, if you wanted to organize that and test what you built, what you actually built, because again, we're going to be taking what you design and we're going to be building it into a flight ready version, but you're still going to have your equipment. You're more than welcome to, do experiments with that as well. And maybe you want to put it up on a balloon. And as I said, we're going to be looking into some other platforms as well that could potentially be available for putting experiments up. All right, so choosing that testable question. What are we even going to make an experiment based on? What kinds of data are we even going to collect? Well, this should be familiar to you guys. Barbie Buckner, if you recall from NASA, was going over the engineering design process. And this is NASA's best version of that. So we're going to kind of take parts of this throughout this presentation and kind of break it down a little bit. So choosing a testable question kind of looks like this. Really, this whole experiment program is going to kind of look like this. You see at the top here, this picture where you've got this whole big scribbled mess at the beginning, and then it's not quite as scribbly in the middle, and then it kind of smooths out and you get a nice straight line there in the end. That's pretty much how this process goes. It's going to be kind of convoluted at first, but as you go through the process, it's going to become smoother. You're going to figure things out, you're going to troubleshoot, and you're going to get a very nice completed project at the end. So let's look at some things that can help us to kind of smooth things out for us. So first thing, first parts of that engineering design process, we're going to ask, right? We're going to identify and define a problem or a question. And then we're going to brainstorm solutions and research ideas. So feel free to take this presentation and use it in your classroom, right? You can just throw it up on the screen at the front of the room, or you can share it with your students, go over it with them, just like I'm going over it with you. And so first things first is, what's interesting? What are you interested in space, in the atmosphere? What do you want to know? What do you want to learn about? What would you like to test? Look at work of others. What have other people done in the past? Can you, add to that? Can you do a comparison of that data or that experiment? See how their data compares to your data. What is something that maybe nobody has ever worked on before, or that you can't find any data or information about? Try to come up with novel ideas if you can. Those will certainly be really interesting. There was that radiation experiment, which was a pretty novel experiment developed by an 11th grader a few years back. That's the one that we went over the data about in the workshop. So one of your students can do the exact same thing. He's actually now working on his PhD in aerospace. So it was a good stepping stone for him, I imagine. That all that stuff definitely went into his college applications. All right, so once you brainstorm some ideas with your students, maybe write them down or create a Google Doc, a shared document that they can add to, then start narrowing your focus. So which questions that your students provide can you, feasibly work on? Maybe some of them would say like, oh, well, let's figure out what the surface temperature of the sun is. Well, while that is certainly an interesting question, this is really not the venue to test that. So just keep that in mind. Then once you have some ideas for questions, you're going to want to see if the equipment is available in order to actually collect data about it. And is it feasible to get that equipment? Do the sensors exist? Can you get your hands on them? Sure, they're sensors that can detect pretty much, anything that the human body can detect, but is it economical, right? And will it fit within the constraints that we're working with? Will, it take too much power, or is it going to be too big or too heavy? So you got to keep that in mind when deciding on the question. Oh, somebody else is coming in. Let me just let them in real quick. All right. Right. Okay. So will the experiment fit within the given constraints? All right. So here are those constraints. So we want to be able to fit within the volume of the CubeSat, right? So if we're trying to fit 6 experiments into a 2U, we're going to give, 1/6 of that, or a third of a 1U to each experiment. So you want it to fit within 3.3 centimeters thick, essentially, because we're going to be stacking these experiments. And then you have 10 centimeters by 10 centimeters as well. The mass, this actually might change a little bit because I just got these 2U cube frames yesterday. So I haven't done the calculation. I kind of fudged the mass by just weighing 2 completed 1Us. So just as I said earlier that, you're going to want to use the most updated version of this presentation. If I make updates to it, I'll send out an email and let everybody know, what I changed, just so you can be, up to date on it as well. Make sure that you can get it done within the program timeline. Power is going to be the total power divided by 6, essentially. So we each have 150 milliamps to work with. Don't put any hazardous materials in there. So we're going to have to get a definitive answer about lithium-ion batteries We still haven't had our preliminary meeting with Blue Origin yet, where I expect to ask those types of questions. But generally, in flight of any kind, lithium-ion batteries or just lithium batteries are considered a hazardous material because if a lithium battery gets punctured, it catches on fire, and so they're probably not going to want that on board of the Blue Origin mission. But I'll find out for sure if like the little coin cell lithium batteries are acceptable or not. A lot of sensors, well, not a lot of sensors, but real-time clocks generally have a lithium battery in them because otherwise, every time the sensor lost power, it would reset the clock. You may not put any living organisms in there, so no animals, insects, no plants. Everything has to be inert in there. And it has to use Arduino because we're going to be connecting all of these together in order to power them. And also we want to be able to have unified data. And so we're going to keep everything Arduino based. So those are our constraints as of right now. Those are subject to change, but nothing on here should change that much if it does. And I'll let you know if any updates are made to these constraints. All right, the logical design. All right, so the logical design is essentially telling us what will the experiment try to accomplish. What is the testable question? Who, the roles and responsibilities in your class or your club have been assigned, and you've written a step-by-step description of how the experiment walks. Interesting. That should be works. No Ewoks here or rice cooking. So we want you to have those three things done and then a written logical design of how your experiment is going to work. Then once you have all of that, you're now going to start getting physical, right? You're going to think about, well, what are the technical requirements for this logical design to be put into practice, right? So what are the sensors and the Arduino boards and the equipment that we're going to be using at that point? You're going to want to have a wiring diagram drawn up, similar to what I was showing you guys in the workshop. The program that I use is called Fritzing, and I will add that to the slideshow with a link. It's a free program. It's extremely useful in making the wiring diagrams, and maybe even at a later meeting, I'll do a little demonstration on how to use that software. I'll show you how to download the different sensors into the software itself, and then how to make the connections and everything, and just some tips on how to use that program. It's very useful when making wiring diagrams. You're going to want to have all of your Arduino code or slash, sketches, as we call them, completed for your physical design. And then you're going to want to have your specifications, written out about what data you're going to collect and how you're going to collect it. And then you will have your physical design. And at that point, if everything is looking good, we can decide, yes, this works, this will fit within the constraints, and this will go on a Blue Origin launch. And then the engineering model build. So this is the actual putting it all together now, right? This is the create part of the engineering design process. So you're going to take your logical design at that point, and you're going to assemble it. At that point, you'll be able to, as you remember from the workshop, do a lot of troubleshooting, right? You're going to be plugging things in. It's not going to work the first time. You're going to realize that you plugged the wrong wire into the wrong spot, or your code is missing something or has something extra, right? You're going to be able to test it out initially. You're going to make sure that all the sensors work and that you're getting the data that you're trying to get, and that you'll be able to then, collect the data about that testable question that you had come up with your students. So at this point, you're going to be able to actually do the testing. You're going to be able to improve upon what you've built. You might, realize at that point that, maybe a certain sensor isn't actually going to work out for you. Maybe you need to use a slightly different sensor. And then you're going to communicate those results mainly to us, but also we want you to be sharing this with your communities, with your schools, your students, parents, administrators. Show them what you're doing, right? I'm sure that if you're making it to this point and you're building an engineering model, it's going to blow away anybody that you show it to. They will be extremely impressed at that point. All right, so I wanted to provide you with some resources to be able to, teach this stuff to your students, essentially. Not every student is going to, or most of your students probably haven't messed around with an Arduino. Maybe a couple of them have, which is great. But you can essentially take what we did in those workshops and, replicate that. This is kind of a wordy slide, as you know from all the slides you've seen that I've made. I generally don't include this much verbiage on a slide, but I wanted this to be basically where you could take this presentation and just use it, or just share it with your students so that they could read through it. So essentially, what this is about is you can buy stuff that, like we used in the workshop, directly from China using AliExpress. If you want to get a lot of things, so like if you want to have one-to-one for all of your students where they all have, sensors and Arduinos and stuff, it might make sense to order that kind of stuff on AliExpress. But just be aware that, just like we experienced during the workshop, if cost is low, failure rate will probably be high, right? It was just an introduction. It was just to kind of get an idea of how Arduino works and how the sensors plug in and how they're coded and everything. What we would recommend is not doing that for your actual CubeSat experiment. Not only because quality is generally low if you're buying it at such low prices, but the shipping time can be long. And we only have a limited amount of time. We don't want you to have to wait a month or more just to get your equipment, and it can take that long. When I ordered all that stuff for the workshops, I think it took at least a month to get everything. Some things came in like a week or two, but some things took 4 weeks or 5 weeks to actually get here because it's coming all the way from China. Here is a link to the workshop presentation. I kind of I polished it up a little bit. I also took out all the differences from the 3 different states. You guys had different presenters and such at different workshops, so I took all that out. So it's just a basic slideshow that we use for the workshop. All right, so here are the sensors that we used in the workshop. Again, feel free to replicate what we did in order to teach your students how to use this stuff. Here is links to all of those parts. So you can actually click on these, and these links will take you to each of the items that I bought on AliExpress. So if you want to introduce using that equipment, feel free to do that. But talking about quality, the cost of the sensor is generally a pretty good indicator, in my experience, of how likely it is to fail. Some of the sensors we used in the workshop were literally only like 50 cents a piece. If you were to buy a similar sensor from a more or a higher quality manufacturer, it could be anywhere from a couple of dollars up to, even I've seen some of the ones that were analogs to what we were using in the workshop for as much as like $20 for a single sensor. You basically get what you pay for, and in every single one of our workshops, everybody learned that the failure rate on some of those things, especially like the real-time clocks and the heart rate monitors, you get what you pay for. I'll leave it at that. But also, higher quality sensors you'll often find will take multiple sensors and combine them into one. So here we have two examples of that. So on the left, we have the BME 280 from Adafruit, which measures pressure, humidity, and temperature. In addition, because it measures pressure, it can do altitude calculations as well using air pressure. So that's essentially a three in one. On the right side, we have a environmental. It's called the Fermion multifunction environmental sensor, and that has everything that the sensor on the left has, as well as an air quality sensor built into it as well that can detect volatile organic compounds and a couple of other gases. So you can save a ton of space by getting some of these higher quality sensors that take multiple things and combine them all into one tiny little package. And there's even more than that. There's another multifunction sensor from DF Robot that I think it has about five sensors on it that can collect up to 11 points of data. So look around and see what's out there. You might be able to collect all sorts of different data points using just a single, little chip. And I have a list on here of recommended suppliers for these types of sensors. Now, not only is quality important, but compatibility is important. And I learned this the hard way. And for anybody who recalls from the workshops, when we were trying to get the accelerometers, the gyros, to work with everything else, we couldn't generally get it to work. And I've discovered the reason behind that is it has to do with the way that a lot of these sensors communicate with the Arduino board. So many of them use what's called the I2C protocol. And if you click on that link, it'll bring you to a page that explains I2C in a lot more detail. But essentially, it's just a method of communicating with the Arduino board. Now, with the I2C protocol, different sensors are given addresses. And what it turns out was going on, and this is a common issue that seems to happen with every accelerometer / gyro and SD card reader. I've had this happen now with multiple different brands from different manufacturers for both the gyros and the SD card readers, where it turns out that for whatever reason, they always seem to have the same address. And so once you try to hook those up on the same Arduino, they conflict with each other, and then you don't get anything from either of them. You can't save any data, and you can't actually collect data from the gyro. Or maybe one will work, but the other won't work. But regardless, it's not going to work out for you. Now, what's cool is certain manufacturers take this into consideration, and they make it so you can change the address of the sensor. So these are, here's two examples right here. On the left, we have on the bottom of the board. Now, some sensors will have stuff on the bottom, like little things that poke out, just different parts of the circuits and such. But a lot of the higher quality ones, everything will be on one side, and then on the back side or the bottom of it, you'll have some options here. So on the left side, you see this AD0 pad. So that's two little metal pads. And if you put a little bit of solder on there and connect those two pads together, what it does is it bumps the address up a number. So like if I think in the example that I was working with, the address was like, they always start with a 0x, and then there's two digits after that for the actual address. So I had like 0x67 originally, but then also on my SD card, it was also using 67. So by soldering these pads together on the back of the gyro, it changed it from 67 to 68, and now they no longer conflict. On the right side, this is the back of that multifunction environmental sensor. it actually it's even more detailed. It actually shows you what the original address is for both of those separate sensors on that one chip. So for the BME 280, it starts as 0x76. Notice how the little circle has the line through the middle, and if you look at those pads, it's identical. But then if you were to cover it in solder and connect it, it would change it to 0x77. And then the same thing with the ENS 160. It starts at 53, but if you solder it together, it goes down to 52, right? So that's just an example of certain sensors that you can change the address on. Now, not all sensors have that functionality, so keep that in mind when you're choosing sensors. If you just don't have that functionality, because since all sensors don't have that, and if there's like really something you want to use, maybe contact the manufacturer before you order it and say, hey, what is the address on this sensor? Because I don't want it to, conflict with something else. If you actually look on the left side, I actually just noticed this down at the bottom. It says default I2C ADDR, right? 0x68. So it actually says it right there on that sensor. So that's something you want to take into consideration if you're going to be putting multiple sensors together. And for whatever reason, it really seems to be an issue with gyro accelerometers and SD card readers. I don't know if like all the manufacturers got together and said we're gonna make this difficult for people and give them all the same address, but that just happens to be the case for whatever reason. All right, and then these last couple of slides have some recommended suppliers. They're not in any particular order. It was just the order that I put them on here. I've been personally working with some Adafruit sensors, where I'm building kind of like a higher quality version of the workshop setup that we're going to be putting on some 0G flights in November. And so I've been using mostly Adafruit. If you want to go right to the source, you can go with Arduino. They are an Italian manufacturer, but they have a lot of stock here in the US. So, you don't have to worry about really long shipping times if you're buying from them. And then DF Robot is a Chinese manufacturer, but they make high quality parts. And that multi-function environmental sensor is one of those examples. And I've worked with those as well, and they're good. The shipping time isn't quite as long as like with AliExpress. I think I ordered some sensors from them and it took maybe like a week and a half to 2 weeks to get to me. But again, if you're crunching for time, you might want to go with one of the other suppliers instead. Also, SparkFun is another U.S. manufacturer. They're based in Boulder, Colorado. They make high quality parts. DigiKey is a well-known distributor of electronics and sensors. They have a lot of industrial parts and such, but they also have stuff for Arduino. Mauser is another U.S. distributor, as well as Parallax. So these are all links that you could go to. And this is not the end all be all. There are plenty of other options as well. You can also order stuff right on Amazon. I've found that sometimes the manufacturer might not have any stock of the sensor that you're looking for. This actually happened with an Adafruit sensor that I was trying to get, and it was out of stock currently. And I looked on Amazon, and they were in stock on Amazon. So some other distributor must have bought up a bunch of their stuff and was selling it separately. You may also want to look at the differences in price between Amazon and these like directly from the source. That might be different as well. If you've got a very tight budget, you're going to want to shop around a little bit. And then also time and shipping. If you have an Amazon Prime account, you might be able to get things delivered in a day, next day shipping for free, as opposed to buying it from the manufacturer where it might take, they might send it USPS and it could take, 3, 4, or even 5 days to get to you, and you have to pay for shipping. So just something that I've run into while, ordering all sorts of different parts and stuff. And that's it for the presentation. The last thing that I would like to do is show you just kind of an example of using some of these higher quality sensors. So this is what I've got here. So this is my SD card reader, my real-time clock. This is my gyro, my UV sensor, and then what is that? And then that's the BME2. Oh wait, this was actually the BME 280, which does the temperature, pressure, humidity, and then this is my gyro as well. So you can see that it all fits in a much smaller footprint than the workshop stuff, but it's going to collect all of the same data. Now, what's even more interesting is this is the Arduino that I'm using. So this is an Arduino Nano Every, as opposed to the Arduino Uno that we used during the workshop. So you can see much smaller footprint. And again, if you can't see my screen very well, because I'm just a tiny little window amongst a bunch of other windows, if you hover over my screen and click the pin button, it'll pin my screen to make it much bigger, be easier to see. So yeah, the Arduino Nano Every is great. It comes straight from Arduino. It's far more powerful than the Arduino Uno. It has more memory, and it's much smaller. So that might be something that you want to try working with. You don't have to, because when we build your models, we're going to be using, we'll probably be using the Arduino Nano Every, or maybe even a Adafruit Feather. But those are both two much smaller, more powerful types of Arduino. All right, so looks like Drea has raised her hand, like such a good student.
And Noah, there are a few questions in the chat too that I can.
All right.
I was gonna just because we used Nano Everys for BattleBots last year, and just to warn people, they are very sensitive. So if you have students who are new to Arduino and they're not grounding things, they literally catch on fire like the second they plug in. But they have the same exact configuration as an Arduino Uno.
Mm-hmm.
So you could have students build big on an Arduino Uno that is less sensitive,
Right.
just so you're not picking up all your equipment.
Right.
I don't know how to mute myself. I can't find it.
I will mute you.
Thank you.
There you go. All right. So Kristen Sims asked, does that volume include power? So on the Blue Origin flight, we get power directly from the rocket itself. So it's basically just going to be a plug that goes right into the Arduino. So you don't have to worry about including batteries or, having batteries take up mass or volume. So don't worry about that. All right. So I think whoever unknown was, if not, AliExpress was a good source. I think if you look on those last two slides, you'll see some good sources. The one on the left, that was the BME 280. And those types of names are pretty standardized across the whole Arduino world. So like a BME 280 is going to be a BME 280 no matter who manufactures it, and it's going to collect the same data. So if that's what you want, you can look, maybe Adafruit has it, but then another company, SparkFun, might have it for cheaper, or it's closer to you, so you'll get it sooner, or whatever the reason might be. Let's see. The Arduino Nano Every is $11 or maybe $12 at this point, right from Arduino. So they're cheap. They're very cheap. It seems like most of the manufacturers of actual microcontroller boards, Arduinos essentially, are all moving towards that Nano Every footprint. Just like with everything else electronic, it gets smaller and better as time goes on, and that's the case with Arduinos as well. Do you end up with conflicts with multiple Arduinos? an easy fix if you didn't have a sensor that had the ability to change the address is, yes, you could just use two separate Arduinos to run the two separate sensors. Now, the main conflict that I have seen, that I've personally experienced, is a conflict between a sensor and the SD card reader. Now, if that's the case, you're not going to want to use two separate Arduinos because you want to actually save that data. So you got to figure out a way to get your SD card reader to work with whatever sensor is having a conflict with. So while, yes, you could potentially get around conflicts by using two separate Arduinos, it's kind of not going to really be useful because if you can't save the data itself. All right, so Jim Lanky asks, do we have to worry about window port for imaging outside of Cube, such as images, videos, UV? So here's the thing. Like I showed you in that picture, that payload locker is not going to really allow for a ton of outside viewing. One suggestion that was recommended by Chris Murphy, some of you met him, he's our balloon guy, was that if you can fit it within the space allotted, you could potentially have an LED as light and a camera on the inside looking at some sort of experiment that you have. Now it would have to be either attached somehow, because you wouldn't want it rattling around inside of there, or would have to have some sort of enclosure. So if you're able to make that work within the constraints, sure. But that's another thing to keep in mind when designing these experiments that are going to be going up on a Blue Origin rocket. It's inside the, first off, it's going to be inside the Nano Lab, aka the 2U CubeSat frame. And then that is going to be inside of an enclosed payload locker. So things that have to do with taking pictures, generally would probably be better on a high altitude balloon or another flight platform. But don't let that stop you. I mean, if you can figure it out, the sky is the limit. Actually, you can go beyond the sky, go out into outer space. Dre, you had another question? Here, I can't unmute you.
I got it. Sorry, I'm not used to using it on my phone, so I just don't know where things are. Yeah, I was going to ask the same thing about being that enclosed space. Do we have to look, if we're trying to look for altitude, do we need to look for something specific since it's a pressurized space?
So we will be
pressure-dependent altitude sensor.
We will be getting data from the rocket itself. So like things like altitude will be included in the rocket's data. So yeah, I've been mulling this over basically since the beginning of the workshops. Like, what are they going to be able to actually collect data on inside of the capsule? So we did those radiation experiments and we showed you that, gamma radiation is going to go right through that capsule. So you can collect radiation, at least gamma radiation. You can't collect alpha or beta radiation because, that's stopped by either a piece of paper or like a pane of glass. But gamma radiation will go right through. Maybe you do want to actually see what the conditions are like inside of that capsule. So you do put those environmental sensors on there. That's perfectly fine. But just keep in mind that you're not going to be getting atmospheric data. You're going to be inside of a pressurized capsule. All right. How do we collect the data from the CubeSat, Leah asks. So include a SD card reader in your design so that you can save that data. What is a good starting list of things to get? All right, yes, solder kit would be useful, and solder. I recommend the Pinecil, Pinecil, is the brand of soldering iron. That's
Know
right.
what? They're sold out. They have been sold out since June. I've been trying to get one, and they said they were going to come back today, and they sold out once they restocked today.
Oh man. Okay. Now this is, I believe this is referred to as a TS100. Let me just double check that. Yeah, TS100 soldering irons are generally the smaller form factor soldering irons. I'll type that in the chat. So if you want to get a soldering iron, I'd recommend one of those just because they're small, they're easy to use. They generally have USB power for them. Make sure that you get the stand. A lot of those don't come with anything besides just a soldering iron itself. So you might want to get a stand. You want to get the tip cleaning stuff. You might want to get a set of helping hands, right? Remember these magnifiers and the little hands to hold stuff. Breadboards. You know what? I'll also put together a list of things, and I'll send that out either tomorrow or Monday, and that'll have like basically the basics of what you'll need in order to get started on prototyping this stuff. Wires, right? Wires you're definitely going to want, and they're called DuPont wires is the technical name for them. Let's see. How long will it be in orbit? So Blue Origin is not launching this into orbit. This is a suborbital launch, which means that it's going to go straight up. It's going to then release the capsule. Once it gets to the highest point, the capsule is going to continue up for a few seconds, and then it's going to slow down, and then it's going to float for a second or two, and then it's going to start coming back down again. So Blue Origin flights are essentially, the most spectacular elevator ride that exists. Goes up and comes back down. Firefly Aerospace, who is launching our Serenity 3U cube, is an orbital launch. And so ideally Serenity will be in orbit for it's around 30 days or so. But these experiments will not be staying up there. And if they did go into orbit, it would be hard for us to get them back. So you would never get to see it again. We will return the experiments to you guys after they have been flown. I didn't think we were going to get the CubeSats back, so I didn't think it would work to use an SD card. Oh yeah, no, yeah, we'll send the data back to you. We'll send the SD cards back to you as well. So we'll build this stuff, and then we'll send you, that equipment. Dre, do you still have a question? Your hand is still raised. All right, Kristen, you have a question?
Yes, I did. You answered a couple of them. I've been writing them down as you talk, but then some people had the same questions. So, with this particular flight in that space, are there Geiger counters that are small enough to fit two? Because the ones I was looking at today doesn't look like two would fit in that space.
You mean two Geiger counters?
If we did want to shield one and not shield the other,
right?
Would they fit?
I mean, it's really all dependent on who you get the Geiger counter from. I don't even know that they still manufacture the ones that we used previously. Our guy Chris, who you know well, he's been looking at Geiger counters in particular to see who makes them and who we can get them from. So I'll share that with you once.
Yeah, because there was one on Adafruit, but it looks like it would fit, but I don't think two would.
Right.
And then the other question I had, the thing that my kids have grabbed onto right now that they're real because they all saw the article about the sound of the black hole, so they're fixated on sound right now. They want to know what space sounds like or what low Earth orbit sounds like, and so but in this application, that won't work within these constraints because we can't get a microphone out.
Well, I mean, I wouldn't be so sure that you can't do that. I mean, I would look into it, see if there are microphones that, I mean, if you think about the microphone that's in your phone, that's probably a teeny tiny little thing. So I don't.
Yeah, there's tons of cool sensors, but if it's inside a box,
I'm sure you will still hear something. I mean,
yeah.
that's it's not soundproof in there. You'll hear the rocket. You'll hear things probably jostling around. Maybe, who knows what you'll hear.
Okay, because I've already done a Google form for them to start compiling their ideas, and that one keeps coming up over and over again. Right.
Yeah.
Thanks.
If it can be done, look it up and work with your students. See if you can make it work.
Okay.
Liz.
Yeah, I just want to add on to both of those ideas. For the dual Geiger counters, we did fly 2 Geiger counters the first time that we flew a 2U with Blue Origin. That particular configuration did take up space. But if a whole lot of people want that data, I think we're open to flying a thing that everybody can use the data from, right? Because we have a lot of different options. And in terms of sound, I have seen people posting sound files on LinkedIn. Here's what the sound is when the Dragon goes to space. Here's what the sound is when New Shepard goes to space. So people are recording this in some way, and they probably have microphones right on the shell of the rocket, but I think it would still be interesting to see what it sounds like from inside. And there's a lot of stuff available now that you can compare that to.
Mm-hmm. Did I miss any of the questions in the chat? I think I got all of them. Does anybody have any additional questions? Okay, well, if there aren't any other questions at the moment, feel free to email me whenever you want. I can answer your questions there. And again, I'm available for one-on-one conversations if need be. What's up, Leah?
I have a question kind of on a separate subject.
Yep.
With the postcards that can be sent up into space, I feel like I saw something somewhere in the information that we had been sent, but then when I went back to look for it, I couldn't find it. So is that the same as going through the Club for the Future?
You know what?
Or-
That just reminded me. I promised that I was going to send a list of instructions for the postcards, and I never did that. So I'm going to put that on my list of things to get done for next week. I'll have the directions on how to request postcards if you don't already have them, how to use the online platform that we use, and how to actually scan those QR codes. So thank you for reminding me. I will have that to you guys next week.
Okay, awesome.
Liz?
And yes, that is Club for the Future. What NOAA has done is to take the Club for the Future cards and add the QR code so that you can track it. But if you want it to fly with Club for the Future, they will fly it. They will track that QR code when they get it. We can also do other things with it. We've got a bunch of them loaded with Serenity. Those won't come back. They're going to go to orbit. But they have been tracked every step of the way. And we've also flown some on balloons and tracked them. It can go on a balloon. As long as we get it back, it can then go with Blue Origin. So you have a lot of choices.
Mm-hmm.
Yeah, I was a little confused. I know it said when I was looking on the website that you could send them in bulk. Mm-hmm. If you send them in bulk, do they mail them back individually? Like if we have postage on the postcards?
So you're talking about directly to Club for the Future, right?
Yeah, I was.
I'm not entirely sure how they do that. I imagine yes, that they will send them back to you, all of them.
I just didn't know how will they know that they're stamped inside the box that I send them in, so they can, like, if we have them all self-addressed stamped.
That's my understanding, because they had us decorating them when we were there for a launch and then dropping them in a special Club for the Future mailbox individually. So yeah,
Just didn't
that's
know
my understanding.
if you sent them in bulk, would they come back in bulk? You know what I mean?
Yeah, there's some video online of them actually going through those postcards and then loading them. So I believe so. I believe they take them out of the box, and if you've got the QR code on them, they have to do that because they got to scan one of them.
They might.
So-
We have to actually confirm with them that they will be able to scan the QR code for us and everything. We haven't actually done the QR code with Blue or Club for the Future yet.
Oh, I thought that Joseph said he would do it personally.
Oh, did he? Then
Yeah, he did.
Then yeah. Then
Okay,
they'll do it.
so definitely wait for your email next week so we can get more information about the QR code.
Yes.
Okay. Awesome.
Pam, you had a question?
I was just going to say, I have a couple friends who have done the postcards and sent them mass, but they have not been returned yet, and they wondered the same thing. So they're supposed to let us know when they get them back and find out how it all works. So as I get information, I'll let Noah know so he can help.
Yep. Much appreciated.
Little piece of inside advice on that. A lot of those postcards were on that launch that just launched and came back. So luckily they didn't burn up.
Right.
And it'll be a question of when are they going to get to launch again.
Yeah, that might all be evidence at this point. Kristen, the next Firefly attempt is going to be at 12:01 a.m. on Monday, and that's Pacific time. So I guess
As Kansas people say, yuck.
Yeah. Us East Coast people also say yuck.
Yeah, exactly.
Yeah, so we'll
Yeah.
watch the video.
Yeah. Yeah. I mean, I'm going to be up for it, but I'm probably going to go back to bed afterwards. All right. Does anybody have any other questions? All right. Well, thanks for your time. And again, get in touch if you have any further questions, and I'll get back to you as soon as I am able. Good luck.
And thank you all. Thank you so much for attending. We're really excited to keep working with you.
Yep.
Thank you.
You're welcome. Bye-bye.